All right, let's look at a specific example of an exponential function. In this case, again, we're always looking for a function in the form y equals a times b to the power of x. So it says in 1983 there were 102,000 farms in Minnesota, but by 1998 this number had dropped to 80,000. So we have to write an exponential function that we could use to model the number of farms that we have in Minnesota. We want to write the function in terms of x and the number, which is the number of years since 1983. Well, if x is the number of years since 1983, then that means if it is 1983 right now, x would be 0. So when x is 0, or during 1983, the number of farms was 102,000. So we have one value right there. Now when it becomes 1998, all of a sudden we've jumped 15 years later. So 15 is our x, and we're at the value 80,000. So we have two values that we can put in here. This value here, because it is where x is 0, that's our initial value. That's where we're starting with. So that's going to be our a value. Then we know the point where x is 15, y has to be 80,000. So we can just plug those in right here. So let's take a look down at their work here and see what they've got. They did pretty much the same thing we did. They plugged in 80,000 for y, 15 for x, and an initial value of 102,000. Now they need to just solve for b. So when they do that, they divide 80,000 by 102,000, and they get 0.78 equals b to the 15th power. Take the 15th root of 0.78, and that should get you about 0.98. Yep, this number right here. So that's our b value. That's what we're growing by. Now, is this going to be exponential growth or decay? Well, in this case, it's going to be decay, because 0.98 is less than 1. It's in between 0 and 1. So it means over time, the number of farms in Minnesota is getting smaller. So the equation that's going to model this is y equals 102,000 times 0.98 to the x. Our initial value, 102,000, times our growth, or that base, of 0.98, which means it's actually getting smaller. That's our decay value to the power of x equals our y. So now it says, suppose the number of farms in Minnesota continues to decline at the same rate. Estimate the number of farms in 2010. Well, 2010 means that it's 27 years later after 1983. So 27 would be our x value that we plug in here. So 102,000 times 98 to the 27th power. Now remember, you want to make sure that you're doing this piece first. 0.98 to the 27th power, then multiply it by 102,000. Make sure you are getting that right on your calculator. You're not multiplying these two first. That would be wrong. So in the end, you should get approximately 59,115 farms. Pretty crazy. So looking at exponential equations and inequalities. Since the domain of any exponential function includes irrational numbers such as the square root of 2, all the properties of rational exponents apply to the irrational exponents. So if we have some expressions here like 2 to the square root of 5 and 2 to the square root of 3, multiplying those together, well, again, remember, if we had 2 to the 5 times 2 to the 3, all we do is add those up and get 2 to the 8. So all we have to do here is add them up, and we get 2 to the power of root 5 plus root 3. Or, let's say we had 2 to the power of 5, that to the power of 3. We would just multiply them and get 2 to the power of 15. Same thing over here. If we have 7 to the power of root 2, that to the power of root 3, all of a sudden now we do 7 to the power of root 2 times root 3, is 7 to the power of root 6. So those are just some properties of exponential functions, exponential equations. So again, one key property then to look at is if we have something like 2 to the x equals 2, notice how in these cases it's the same base, 2 and 2, to the, let's say, 15 or so. Well, it's the same base, so we can essentially just kind of cross those out, so x has to be 15. So that's that'll be a helpful property when we're looking at some of these. So if we wanted to solve something like these examples here, if we have 3 to the 2n plus 1 equals 81. Well, we can't solve that right away because those don't have the same base 3. But we can switch 81 over to a base 3. 81 is 3 to the power of 4. And over here we had base 3. 3 to the power of 2n plus 1. So now all of a sudden we can cross out those 3's and just say 2n plus 1 equals 4. Subtract 1 from each side and we're getting 2n equals 3. Thus, in the end, n equals 3 over 2. Let's try that again. If we've got 4 to the power of 2x equals 8 to the power of x minus 1. Well, in this case, we can't get 8 to a power of 4. We can't get 4 to a power of 8. We have to find something that they both work as. Well, 4 we can call 2 to the second power. 8 we can call 2 to the third power. Now we've got everything in powers of 2. So if we solve this out, on our left side, 2 times 2x is 4x, so we have 2 times 4x, or 2 to the power of 4x. Over here we have 3 times x minus 1, so we'd have to distribute that across. Well, actually, should I say, in the end here we have 2 to the power of 3 times x minus 1. Now, they just cross out the 2's here and leave our 4x equals 3 times x minus 1. Now they distribute and get 3x minus 3 equals our 4x. Subtract 3x from both sides and we just get x equals negative 3. Pretty nifty. So now we have some more properties here. If we're looking at exponential inequalities. So if b is going to be greater than 1, then b to the power of x is greater than b to the power of y if x is greater than y. And b to the power of x is less than b to the power of y if x is less than y. So if, for example, if 5 to the x is less than 5 to the 4, then x has to be less than 4. So think of an example when that would work. Let's say x equals 2. 5 to the 2 is less than 5 to the 4 because 2 is less than 4. Which works out because 5 to the 2 is actually less than 5 to the 4 and 2 is actually less than 4. So how would we solve these kinds of equations? If we have 4 to the 3p minus 1 is our original inequality. Well, we have to rewrite this 1 over 256 so we get it into base 4. Now again, remember properties of exponents. 1 over 256 is actually 4 to the negative 4th power. So now we have the same base 4 on both sides. So again, we can essentially cross out the 4. That leaves us with 3p minus 1 and negative 4. 3p minus 1 is greater than negative 4. Just add the 1 on both sides. So now 3p is greater than negative 3p. Divide each side by 3. P is greater than negative 1. And again, if we wanted to check that, we just plug in something that's greater than negative 1, like 0, and it should hold essentially then. So 3 times 0 is 0 minus 1, so 4 to the negative 1 is 1/4, which is in fact greater than 1/256th. So it works. All right, last slide. We have, we need to write an exponential equation given two coordinates. We have 0, negative 2, and negative 2, negative 32. And we're looking for an exponential equation in the form y equals a times b to the power of x. Well, remember, whenever we have an x equaling 0, this value here is our initial value. That's our a. So we can replace that one right away and say y equals -2 times b to the x. And then over here, these give us our x and y values that we can plug in. So I'm going to change this x value here to that x value of -2, and change this y value here to our y value of, oops, I want a blue, -32. Now, all we have to do is solve for b, and we will have our exponential equation. So if we divide both sides by -2, that leaves us with positive 16 equals b to the -2 power. If we want to get b to the first power, so it's just b alone, we have to take both sides to the power of -1/2. Because -2 times -1/2, over here, 16 to the -1/2, -2 times -1/2 equals 1, so it will just be b. Now, we need to solve for 16 to the -1/2. Well, 16 to the 1/2 is just the square root of 16, so it would be 4. But since we have that negative out in front of it, we have to do the reciprocal. So it would actually be 1/4 equals b. So our b value is 1/4, which means our equation in the end, a equals -2, that initial value, and then our b value is 1/4 to the power of x. Now, notice we can't simplify to y equals -2/4 to the power of x. This we cannot do because of order of operations. We have to do our exponent first before we multiply. So you can't simplify it. So this is our final equation as simplified as it's going to get.